All right, so now that you guys know how to solve for the value of KEQ, and you know how to solve problems like ice tables using the value of KEQ, in all of those situations, we were presented with an initial concentration of reactant, and you probably had 0 for the molarity of the product. And those problems are easy to set up if you just follow the ice table format. However, there are going to be times where you have initial concentrations of everything and it's not clear which side that you're going to add the value of x to and which side you subtract. So, for example, here, in this PCl reaction, PCl3 and Cl2 are our reactants, and PCl5, that's our product. But if we have initial concentrations for everything, I don't know how to fill out the ice table. I don't know whether I should be adding or subtracting to the left or to the right side. So when this happens, you need to set up what's called a reaction quotient. And the reaction quotient follows the same format as KEQ. It's still products over reactants, but the difference is that the concentrations that you are using are specifically initial concentrations. And because they are initial concentrations, this is now just set equal to what we call Q, not KEQ, because this is not at equilibrium. So by plugging these values in, if I take the PCl5 and put it here, and put the PCl3 here and the Cl2 here, by plugging everything in, we get a value of 10. So 10 is our current reaction quotient. It is the current ratio of products over reactants. So the next thing we need to do is we need to compare the Q value to the KEQ value. So if the Q value is less than KEQ, that means there's too little product, right? You're starting off with not enough product, and then the reaction will go forward to make product. Whereas the opposite is true. If Q is greater than KEQ, so you start off and you have too much product, well, then it stands to reason that the reaction is going to try to break up some of that product and make more reactants so that you get back to equilibrium. So, hypothetically speaking, let's say that KEQ, I'm just making an arbitrary value here. Let's say KEQ is like 2.5. In this instance, Q, which is 10, is greater than KEQ, which is 2.5. So that means we're starting with too much product. And therefore, the reaction will go backwards. So if it moves backwards, that means in your ice table, you will be adding to the reactant side, and you will be subtracting from the product side. And that is the whole reason why we use Q, right? We solve for what Q is initially. We determine, we compare it to KQ. If it's bigger than KQ, you have too much product. That means you must go backwards, and going backwards means adding to the reactants, subtracting from the products. If Q is smaller than KEQ, that means you have not yet reached equilibrium, so you don't have enough product, so you would be making product, and in that case, you would be adding to the product side.